see and hear me. If not, write in the chat. And Federica told me there are a couple of questions, so if she can read them to me.
What kind of maintenance Virgo require?
So the maintenance that Virgo requires is continuous. When we are data taking, because basically, let's go one step back. Virgo is not taking data all of the time in all the years that it has been active, but even after the detection of gravitational waves, Virgo has not been taking data the entire time. The way this works is that we take data for a certain amount of time, usually about a year. Then we do technical upgrades to better the machine, so to better its sensitivity, to make us able to see more and see further in the universe and pick up more signals. We do these upgrades, then there is a phase, which is the phase in which we are right now, that is called commissioning, because actually you do all these technical upgrades from our hardware, from our software. Sorry, let's move. Some are hardware, some are software. We do all of these upgrades. And the idea would be that then we turn on the machine and the machine just works. But that's not realistic. That's not how it works. The way this works is that when we turn it on, we have to fine tune it, basically. We have to make sure that all of those things that we upgraded, that we changed, that we made better work together. So that phase is called commissioning. And that's the phase we are in right now. To answer your question about the maintenance, so this is a sort of maintenance, but it's not just a maintenance, it's a bettering of the experiment that is done basically continuously. We do data taking and then we do upgrades and then data taking and then upgrades, etc. But during the run, while we are taking data, we try not to touch the detector itself. We do maintenance once a week on Tuesday morning, and that's basically just cleaning. But we never open the towers. We don't go and touch the mirrors unless there is a problem, there is an issue. But if there are no issues, most of the maintenance that is done during data taking is just cleaning. And in case some small things need to be changed, to be upgraded. But basically, the main point is that if we have to open some vacuum, so if there is a tower that is in vacuum and we have to open it, that takes a lot of time. So it is only done if there is a big problem. Otherwise it tends to not be done. So for that year of data taking, the maintenance is very minimal. Of course, there is always someone in the control room 24 hours a day, because we need to take data, we need to control, we need to make sure, but it's some sort of control that is done remotely. So the control remotely is continuous, 24 hours a day. But the maintenance inside the experiment is very minimal during data taking. I hope I answered the question.
Yeah.
There is another one?
Is the frequency of the laser bigger than how size you need to measure?
Okay, and maybe there is another one on the frequency you were telling me? So I answer about the frequency in general.
No.
Okay. So to answer about the frequency of the laser, so the frequency is that of infrared, and that is, so let's talk about wavelengths, because wavelengths are a measure of length, and so they can be, we can compare them to a length, because we are here measuring the length. So the wavelength is bigger than what we are trying to measure. So we're trying to measure something that is smaller than the diameter of a proton, while the infrared wavelengths are between nanometers and millimeters. So the wavelengths are bigger, but it is true that there is a link between the frequency of the light, of the laser, and the detection of the waves. So ideally, it would be better, and forgive me if I don't go into detail on the why, because it's quite a complicated explanation, but it would be better to use a higher frequency laser, so a laser that has a smaller wavelength. It would be the wavelength closer to the dimension we're trying to measure would be better. But the reason why we don't do it is that would that would have technical difficulties because it would have more energy, and having more energy traveling inside the detector is a problem. Compared to the same beam, if we had exactly the same beam but a higher frequency, we would have higher energy, and that is a problem because all the optics eat up, and all the heating creates noise. So it is a compromise. What we have to find is a compromise between what would be best, which is ideally, theoretically, if we were to do this on paper, which is a higher frequency laser, and what is technically doable. And the lights went off, but don't worry because now we will move. And the comparison between those two things means that infrared is the best wavelength. Other questions?
Yeah. Where exactly is the attenuator located? Outside of the Virgo's two arms, and each mirror requires an attenuator, or is one sufficient?
No, it's one for each mirror, and I will answer this question in a second because it's much clearer when we go inside. Other questions? Okay, then let's start moving inside. Before we move inside, I want to show you something that I think will be, I think it's their motion sensors, that I think will be useful as we go inside. Sorry, let me check the time. Which is that I have lied to you a bit. No, just kidding, I have not lied to you, but I have simplified the components of Virgo. Because I told you that Virgo is in theory, the same as that model that I showed you. And that model that I showed you has very few mirrors. It was just the central mirror, and then two at the ends. There were just three of them. Those three, and then they had a source for the laser and a place where the laser is collected at the end. So it would be 5 towers, right? The beginning, the middle, where the beams are split, the two ends, so 4, sorry, and then the detection tower. So that would be 5. Virgo has many more towers. And these many more towers are because Virgo is a better version of a simple interferometer. It has more instruments, more tricks to help us detect gravitational waves. These do not change the functioning of the detector in a fundamental way. But they help the sensitivity, and they require more towers. So as we go inside, you will see more towers than those that you expect, which are only these 5. And I want to show you a model, like a map of what you will see, so that you know what to expect. So we also do, we revise a bit what we said right now. So we have a laser source. It starts. It goes here to this cavity that is actually outside, so we will not see it here. It's called the input mode cleaner. It cleans the beam, basically. Then it continues, and the first mirror it finds is this one. It's called power recycling, and we will see what it does at the end. Let's ignore it for now, but the first mirror that it meets is this one. But as it moves this way, it will pass it. It will just go through it. It goes through it, and then it gets here, and it gets to the center. This is one of the mirrors that you expected, the beam splitter, the central mirror. It goes to the center, and then it moves to one arm and the other, so it splits in two. Here, it first finds 2 other mirrors, and these 2 mirrors create cavities. So there is a cavity here and a cavity here. In here, the light travels hundreds of times. So it doesn't just go to the end and back. It goes to the end, and then it goes back, and it meets this mirror, and so it goes back to the end, and back here, and back, etc., for hundreds of times. And then after a few hundred times, it goes back to the beam splitter. So these are 2 additional towers that we will see inside. And why does it do this? It does this because in this way, we artificially lengthen the arms of Virgo. Basically, instead of having 3 kilometers arms, we have 3 kilometers times 300, 500. So it's a trick to make them longer than they would be, because the longer the arms, the more sensitive the detector is. So these are 2 mirrors that we will see inside, and then it goes back to the center. When it goes to the center, The beam splitter puts the beams together again, but in two directions. So one of them goes to the detection and is detected, and it's we see if there is a gravitational wave or not. The other alpha would go back to the source, and it would be lost. That would be a waste. So we put this mirror here that is called power recycling, so that it recycles the power. And a similar thing is done for the signal recycling mirror that is just in front of the detection. So it's in front of the tower that detects gravitational waves. So you will see all of these mirrors inside here. You will see the source, the central one, the detection, which are the three that you were expecting, but also the power recycling, the signal recycling, and these two towers and mirrors that are at the beginning of the arms. So this is quite more things. But again, it doesn't change the basic functioning of the detector. I think a good metaphor to understand this is if you have a car, you can have a very old car. I don't know, maybe you think your grandpa's car that is like 30 years old, and it's just a wheel and the wheels, and then you sit and it has just the basics, but it's a very basic, very old car. And then you take a Ferrari. They are the same thing. They are two cars, but one has a lot more details, a lot more mechanical things that help it go faster, that help it be safer, that help it do what it needs to do. So that's basically the difference between a basic interferometer and what Virgo is, and it's the reason for all of these additional pieces that we will see inside. So let's go inside. Meanwhile, we have to walk for a bit. So if any questions come up, there is one already. Okay.
We'll speak about the black holes that produce this wave.
Yes, we will. We will in a second. So we will move inside. To move inside, we have to wear some protection because basically we want to avoid dust from getting inside as much as possible. So on our shoes, we will wear these covers. So now I will wear mine, and then I will let Federica do the same. 1 and 2. Voila. So that's it. Okay, so we can go inside. And we go upstairs. Okay. So this is the central building of the Virgo interferometer. Here are all the towers. And here I can answer that question about where the super attenuators are. Yes, each mirror requires a super attenuator. And that's why you see so many towers. Maybe Federica can show you. And if we move in here, we can see all of them. I told you that they would be more than expected. Each of these towers that is very high, it's about 12 meters high, if I'm not wrong, contains a super attenuator and at the end, a mirror. So each of these contains one of those towers that you have seen at the beginning of the tour, and suspended to it at the end, there is a mirror. You can also see on the wall a big sign that says laser hazard. For us, in this moment, the laser is not a hazard, but this is quite a picturesque part of this room. But of course, it has also a safety reason, because if the towers were to be open and the laser were to be on, we would have to wear safety goggles, because our laser is powerful enough to damage the eyes. So people who work in here have to mind these safety measures. So since there was a question about this, let's say a few things about the objects that generate these gravitational waves. So of course, this is a tour of the detector itself, so we do not spend a lot of time talking about this, but of course, the point of what we do here is to do astrophysics, is to study, as we said, these gravitational waves. And what gravitational waves do is that they give us information about the objects that created them. And the objects in question are, for now, the objects that we see gravitational waves from now are black holes and neutron stars, which are very, very, very massive objects in the universe, the most massive objects in the universe. And when they, as we were saying, collide with each other, when they merge, when they fuse, they create these gravitational waves. From gravitational waves, so as you know, black holes are quite hard to see. There were recently some pictures of black holes, and these pictures were so special because seeing a black hole is hard, because black holes don't let light escape, basically. So from gravitational waves, we have been able to see a quantity of black holes never seen before. And so we have been able to do what we call population studies. So to know, on average, those black holes, what do they look like? What is their mass? Where are they located? And how do they merge with each other? What is the dynamics of them merging with each other? And this is even more important for neutron stars in a way, because contrary to black holes, neutron stars do also emit light. And since they emit light, they can also be seen, some light can also be seen from their encounter. So when they merge with each other, they emit light. And so it is possible to do what we call multi-messenger astronomy, which means astronomy from different messengers, both gravitational waves, light of many kinds. As we said before, light is a spectrum, and also particles, so neutrinos, gamma rays, etc. This is the beauty of what we can do here with gravitational waves. Multi-messenger astronomy is the frontier of astronomy, of astrophysics at the moment, and so the importance is to be able to give very quick alerts to all telescopes around the globe. This has already happened in 2017, where Virgo and LIGO have seen the merger of two neutron stars, and immediately an alert was given to all telescopes around the globe, who pointed their lenses at the sky in that exact direction, because having 3 gravitational wave detectors allows to do localization, so to know more or less where the wave is coming from. And so all the telescopes were pointed in that direction, and they could also see the light. They could also see what came from that interaction. So we were able to do multi-messenger astronomy, so gravitational waves and light in all the spectra. And this allowed us to know so many new things about neutron stars and what they do when they collide. For example, there was this theory that the fusion of neutron stars with each other, so the merger of neutron stars, was the origin of heavy elements in the universe. This was a theory, but it had not been proven before 2017. With that observation, we were able to prove that they do generate heavy elements, because the telescopes saw the traces of light emitted from those heavy elements. And for example, one of them is gold. So we discovered that gold is made in the fusion of neutron stars. Before, no one knew for sure where gold came from. We knew where to find it on Earth, but how did it get there? What created it? And we found out that fusion of neutron stars created it. So this is just an example, but so much new astrophysics can be done with these instruments. So before we move to the next step, which is also the last step, I ask you if you have any questions now. maybe while we go out. And if you don't, then you can write them as we move to the next step, and we will read them when we get there.
Yeah, one question. How do you manage to let the light exit the Fabry-Perot cavities?
Sorry, I didn't get the beginning.
How do you manage to let the light exit the Fabry-Perot cavities after 100 reflection?
Yes, exactly. So yeah, this is a very good question. This is an optical effect. It depends on the lens, on how the lens is made. So there is not a person that counts. Of course, I say this as a joke, but your question is a very smart question. But it would be impossible to have a mechanism that counts. Oh, this photon has passed the 200 times, now it needs to escape. Of course, that is not feasible. It's the way that the optic is made. So the way that the mirror is made, in the same way that, for example, the beam splitter is made to split the two beams, that mirror is physically made. It's a very optical matter. It's physically made to have a percentage of reflection versus transparency, basically. So most of the times it reflects. So when the photon comes back, it is reflected. But a very small percentage of the time, it is transparent. It makes the photon escape. And so it's a statistical matter, basically. Every photon, if you want to think of light as a photon, statistically will stay in that cavity for a certain amount of back and forth, and then it will escape. There is, of course, no count, so it's not that every photon has to do a certain amount of steps. Other questions? Okay, we will start moving towards the outside, and I will see again if there are questions in a bit as we start moving outside. Okay, so I see there are no new questions. We will now move to the control room, which is our last step. So we will again lose connection for a minute or two. So be patient for a little bit as we move to the control room. Okay, so now I'm talking a bit less high volume than before because we are inside the control room of the Virgo detector, where some people are here working, so we don't want to disturb them. So this we want to share this space because this is the brain of the detector. This is where we control the machine, where the people who are constantly here working now, as we were saying, on the commissioning, but even during data taking, there are always people here working on controlling the machine and making sure that everything runs smoothly, that if there are some problems, they can be solved, they can be attended to, and that Virgo stays in its function and detects gravitational waves. And in this moment, to make sure that the commissioning runs smoothly, so that all those parts that have been upgraded can be made to work together. So I want to show you a bit the screens that we see, and I ask Federica to do a bit of zoom for me so that they can see. So at the bottom of the screens, you can see a series of webcams that show basically parts inside. There are cams inside the interferometer showing us the beam, the light beam. So this is the light beam in different points. And of course, the people who work here from seeing these images know how the interferometer is behaving digitally. While on the top screens, you can see on the right a few graphs that show the, the function, the two laser beams, basically the intensity of the beams. And on the left, there is a table that you can see there is some green, there is some red, there is some yellow. And those are all the subsystems of the detector. And so from that table, they can have a general look of what is working, of what needs attention, of what of how all the subsystems are working together and are functioning at the moment. Of course, now not everything is working perfectly, but as we said before, now we are in a phase of commissioning, so we're not taking data at the moment. So these are basically the screens that the people working in the control room have at their disposal at the moment. So now we will exit, and I will leave you one last time for questions, if there are any. Maybe let's move to here. So we have the peace to answer our questions.
So we have, as per Google, 35 gravitational waves were detected by Lagrange Virgo. Is that correct?
So what you are finding on Google is one release, which is the latest release of the gravitational wave detected in the last period, which was actually half of a period, half of an observing round, basically the second part of the third observing round. That's where we detected 35 gravitational waves, but the total number is 90, almost 90. So in total, 90 gravitational waves have been detected so far by the LIGO Virgo collaboration.
Okay. When will start the next measure for?
So for now, the plan is to start in March of 2023. That plan is at the moment under review, so we will see exactly if that will be the start date or not, because all the detectors are in commissioning, and of course there have been some delays due to world events. But we hope that anyway it will be at the beginning, in the first half of 2023.
And then what are the improvements for the next one?
So quite a few improvements have been made. Sorry, quite a few upgrades. So what has not been changed for now is the mirrors, because the mirrors will be changed in the next upgrade phase. So the power of the laser has been increased because makes the sensitivity better. Another thing that has been added is a cavity to control what we call quantum noise, which is a noise due to the quantum nature of light, which is a very, very, very small disturbance, but to the sensitivity that Virgo gets to, even the quantum nature of light starts to be a disturbance. So a new cavity, a new 3-kilometer cavity has been added to improve the sensitivity to do what is called the squeezing of light, which means that before entering the detector, light goes in this cavity, and it is squeezed, meaning that it is manipulated, and the quantum effects that it would have that would disturb Virgo are controlled. Of course, they can't be cancelled because we can't cancel quantum physics, but they can be controlled to improve the sensitivity a little bit. Another thing that has been done is that the control of the noises due to some internal, for example, some conditioning, some heating, because of course the central area of the interferometer has to stay at a fixed temperature. So there is a lot of air conditioning to do, and that creates noise. And so there have been actions done on the on those systems to decrease the noise that they make, because that was a noise for Virgo, and it is still, but less. The level of the vacuum has been improved due to some practical interventions done on the towers. The signal recycling mirror has been added that I told to you about before. It wasn't there before, so a completely new tower mirror has been added. I think these are the main ones, but of course, many smaller things. Other questions? So while you think of maybe the last minute question, I want to remind you before we say goodbye, is that you can follow us on social media. We are on Facebook, on Twitter. So on Facebook, you can find us as Ego and the Virgo Collaboration. On Twitter, you can find us as Ego Virgo. On Instagram, we have a shared Instagram profile with LIGO called LIGO Virgo, and also a profile in Italian called Ego Virgo Waves. So on Instagram, you can even choose the language if you prefer English or Italian. So if you do follow us on social media, you will find a lot of updates about what we do, a lot of videos, a lot of content with explanations of the science of Virgo and of gravitational waves. So if you were interested in this visit, which I hope you were, you may find more on our social media. So I encourage you to follow us. More questions? Yeah?
The more the sensitivity, the more the distance of the objects we can sense.
Exactly. That is exactly the point. We measure the sensitivity in distance. So we measure the sensitivity in megaparsecs, which is a unit of distance, of astrophysical distance. So it was 60 megaparsecs in the last run, and we hope to increase the sensitivity up to 90 megaparsecs in the following run, because yes, exactly as you say, more sensitivity means being able to detect fainter signals, and fainter means that they come from further away, but also fainter signals within the area that we could already see, basically. So yeah. Okay, I think we no longer have questions. We do? No? Okay, thank you very much. We do not have any more questions. Again, if more questions come to mind, you can contact us on social media and we will do our best to answer. Thank you very much for being here, for listening to this, for signing up for this. And I hope one day I will see you here in person at Virgo, because we also do in-person tours. So if you pass from Pisa, come visit us. Bye, have a nice day.
Thank you.